Today we'll be starting off question 1 of section 1.2, which reads as follows. Verify that the operations on pairs of natural numbers defined in equation 1.22 satisfy the same associative, commutative, and distributive laws as do the corresponding operations on the natural numbers. And these operations are compatible with the equivalence relation on these pairs, in the sense that equation 1.25 holds. So there's a lot here, so take a second to read all of it. Some hints are already provided for you, so we won't take a break for those. Great, so let's begin. And so we're going to jump right into the proof, and this is just a simple verification question. So we're just going to start with verifying each of the things it wants us to verify. In doing so, we'll note that if you read through the text, it actually gives you the proofs for the associativity and distributivity of addition over multiplication and the associativity of multiplication in these two lines. So we see that we don't need to prove those. So we'll also note that we have the equivalence relation defined in this way, that two elements are equivalent to each other if these particular sums hold. So let's actually take it from the equivalence relation in the sense that equations 1.25 holds, and that's this equation, or these pair of equations. So we can check that. Namely, for this one, we have a1 plus c and b1 plus d. And we're going to check if that's equivalent to a2 plus c, b2 plus d. So the way we check that is it's true if and only if a1 plus b2 is equal to a2 plus b1. So we see that we need to check if a1 plus c plus b2 plus d is equal to a2 plus c plus b1 plus d. And it's equivalent to asking, if we apply cancellation, these c and d are reflexively equal to each other. This is equivalent to checking that a1 plus b2 is equal to a2 plus b1. But we know this is true because we are given that a1b1 and a2 b2 are equivalent. So that gives us the first one, and then we can check the second one by applying the definition. So we get a1c plus b1d, comma. Let's see what's the second element. It is going to be a1d plus b1c. I need to check if this is equivalent to the same operation applied to a2, b2. So again, the way we check that is we check the equivalence. So we check if it's equivalent to checking if a1c plus b1d plus a2d plus b2c is equal to a2c plus b2d plus, and then it's going to be b1, so this is a1d plus b1c. So we need to check if these two are equal. Well, we can check this by noting that we know that a1 plus b2 is equal to a2 plus b1. And we see a1 and b2 both have a c coefficient on the left hand, so we replace that with a2 plus b1c, and that's going to be equal to a2c plus b1c, so those match. And then we have b1d plus a2d, and we see that that's going to be the same as a1 plus b2, and we see that that matches the d term here. So in fact, these are equal, and therefore they're equivalent, so we have that equation 1.25 is holding. And while I erase this, you can continue to try to predict what we're going to do next in the proving that the laws on addition and multiplication are obeyed, or you can start them yourself, or you can just wait while I finish erasing this small section here. So let's proceed with the addition, and let's try to prove the associativity. So that means that AB plus CD plus EF is equal to, and let me put some parentheses in here, put this outer pair here, is equal to, and then if you move the parentheses like this in the standard associative way. So let's start with the left side, and we get a plus c, comma b plus d, and this is plus ef. But clearly that's just equal to a plus c plus e, comma b plus d plus f. And now we can apply the associativity of addition in the natural numbers to rearrange things within this expression to write this as a plus, and I write this as c plus e with some parentheses around it, and then b plus, and then d plus f with some parentheses around that. And then we split the sum, and we see we get the solution of ab plus the quantity of cd plus ef, and we have associativity. We have associativity of the multiplication proven here. So let's jump ahead to commutativity, which is namely, we want to prove that a comma b plus c comma d is equal to c comma d plus a comma b. And we do this by taking the left-hand side, and we get a plus c, comma b plus d, and then we apply the commutativity of addition for the natural numbers to get this as should be c plus a comma d plus b. And you'll note we're dropping parentheses here, but they should be written out. With this, we then split the addition in the standard way, and we get this side, so we have equality. Next, for multiplication, we're going to do a very similar thing, but this time we're going to apply the associativity, the commutativity of multiplication of natural numbers to simplify it. That is, we apply a definition of 1.22 to get a comma b times c comma d is equal to the quantity of ac plus bd ad plus bc. And it may be useful to write out the other multiplication to see how we should rearrange things. But, and let's do that now, where we say c comma d times a comma b. And so how we should rearrange this is to write this as ca plus db. Sorry, should be a d first, because in our product we have d first, plus db, comma da plus cb. And that's just by applying the commutativity of multiplication in the natural numbers to get this form, and then it's very easy to see this equals this form, so we have commutativity. We've already proven distributivity, and we've already done the rest of the question, so this is actually where we're going to be able to finish. Thank you for watching.